everybody. In this video, we're going to start talking about three-dimensional solids. But before we talk about three-dimensional solids, let's start at the beginning with a zero-dimensional object, one of our basic building blocks of geometry. So a point is shown below, and by now you all know what a point is. It has no size, no width, no length, and no depth, so we call it 0D. And here we have a line. A line is one-dimensional. And as we know, a line extends infinitely in both directions. That's why it has arrows on both ends. The one dimension that lines have is length. And when we have multiple points on the same line, just a review of some vocabulary, like points A and B here, we call them collinear points. And here we have a plane. A plane is two-dimensional. It has no thickness, but it has length and width. And a plane does extend infinitely in both directions. So sometimes instead of seeing it drawn as a box, you will see it drawn with arrows on the ends to indicate that it does extend infinitely in both directions. And just like with a line, you can name a line with any 2 points. With a plane, you can name a plane with any 3 points that are not on the same line. So for example, on this plane, points A, B, and C, they're not on the same line. I can't draw a line through all of these points at the same time. So I can name this plane ABC. There are 3 non-collinear points on this plane. So before we move forward, let's talk a little bit more about planes. 2 points determine a line. What determines a plane? 3 points determine a plane. You can have 3 points that are not on the same line. They can just be 3 separate points, like you see here. We can have 2 points that are on the same line and 1 point that's not, as long as they're all not on the same line. Over here, as we can see, we can have 2 lines that intersect. As long as we have any 3 points that are all not on the same line, it determines a plane. And here's a better representation of a plane, this gray square over here, just so you can get a better sense. And notice over here, we have a line that is perpendicular to the plane, forming 90-degree angles with it. We have some lines parallel to the plane and some lines parallel to each other. I also want to mention skew lines. Skew lines are lines that are actually in different planes. They are not parallel, but they do not intersect. So if you take a look at the 2 lines here, they're not parallel to each other. And if they were in the same plane, they would intersect. But since they're in different planes, they don't intersect even though they're not parallel, so we call them skew lines. Now we're going to start talking about three-dimensional solids. And the thing that makes three-dimensional solids different from two-dimensional solids is that they have space. You can think of space as the inside of a box. You can put things inside, you can fill it up with space. So we're going to talk about a couple of ways that we can go from 2D objects to 3D objects. And I should mention that if shapes have space, then that also means that they have depth, which is our third dimension, or height. If it's going down, it would be depth. If it's measured upwards, it would be height. So our 3 dimensions of a three-dimensional solid are length, width, and height, which is the same thing as depth. So as you can see here, if we start with 2 bases that are parallel to each other, we can make a 3-dimensional solid. And over here, as you can see, it is a cylinder in this picture. We also have prisms, which are made from parallel bases. If you take a look at the prisms here, notice how the bases are parallel to each other. And something to keep in mind, our prisms are named by their bases. So over here, this is a triangular prism because the bases, the top and the bottom, are triangles, as you can see. Here's a little bit more about cylinders. We have two types of cylinders, right cylinders and oblique cylinders. What do you think is the difference between right cylinders and oblique cylinders? Here's a couple more images of prisms. So we talked about triangular prisms with the triangular bases. Rectangular prisms have rectangle bases. Pentagonal prisms have pentagon bases. Hexagonal prisms have hexagon bases. So once again, prisms are named by their bases, and the bases are parallel to each other. We have a couple of properties of prisms. We have vertex points, that's the corners, faces over here on this cube, that is the squares, and edges. Those are the lines that connect vertex points together. The second way, besides having parallel bases, that we can go from a two-dimensional shape to a three-dimensional shape is through a rotation. So we're going to imagine that we're taking the rectangle here and that we're rotating it really, really, really fast around this line, so fast that we get a three-dimensional solid. And if you take a look over here, if we start with a rectangle and we rotate it really, 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 really fast around the point, it becomes a cylinder. So you can visualize this as well with a piece of paper. If you take a piece of paper and you fold it, you get a cylinder. It's the same thing as rotating it really, really fast around the line. So for A and B, since we're making 3D solids from rectangles, we know that they're going to end up being cylinders. They're just going to be cylinders facing different directions because we're rotating around. Because the rectangles that we're starting with are facing different directions. This one's standing up, this one's horizontal. So when we rotate it, we get this kind of cylinder. And when we rotate it this way, we get a wider cylinder. Over here, we have a triangle, and it tells us that this triangle is a flag on the flagpole. And we want to know what 3D shape we get from rotating this triangle really, really, really fast around the flagpole. So when we take a triangle and we rotate it really, really, really fast around the line, we get a cone. I'll do that one more time so you can see it again. Yeah, a cone. So this triangle is going to be a cone when it becomes a 3D solid from rotating around the flagpole. And over here, we have a circle that's being rotated really, really fast. And when we rotate a circle to make a 3D solid, we get a sphere. Let me do that one more time slower. There we go. And you can also visualize that by thinking about a coin spinning really, really fast. A coin is a circle. And when you spin it really, really, really fast, you end up with a sphere. It kind of looks like a sphere. And here's an image of that from Google Images. When the coin spins really, really fast, even though it's a circle, it starts to look like a sphere, like a 3D solid. So you can see that from this image here. Other than parallel bases and rotations, our third way to go from a 2D shape to a 3D solid is by starting with a base and going up to a point. And as you can see here, we have a cone when we do that, because a cone has a point, it has a base, and it has a point. So a cone that has a circle base is called a circular cone. So here we have a right circular cone, and we have an oblique circular cone. Once again, the difference between a right circular cone and an oblique circular cone is that when you draw a line down from the point, it makes right angles. Here in the oblique one, when you draw a line down from the point at the top, it does not make right angles. And if we have a cone that has a polygon other than a circle, because a circle is not the polygon, but that has a polygon for a base, is a pyramid. So over here, notice that this would be a rectangular pyramid because it has a rectangle bottom. And this would be a pentagonal pyramid because it has a pentagon for the bottom. So just like prisms, pyramids are also named for their bases because their bases can be different shapes. But the difference between a prism is that a prism has parallel bases and it has two bases. There's one on the top, one on the bottom. A pyramid only has one base, and at the top is a point. The last thing we're going to briefly mention in this video before you see some practice questions is something called a cross section. So we get a cross section when we slice a 3D solid with a plane to get a 2D shape. You can think of it kind of as like cutting out a piece of the solid. So over here we have a pyramid, and if we cut it parallel to the base horizontally, notice that we get a rectangular cross section. But if we take that same pyramid and we slice it perpendicular to the base vertically, notice how we get a triangular cross section. So you can get different cross sections from the same 3D solid depending on the way that you slice it, whether you slice it horizontally, whether you slice it vertically, or whether you slice it in some completely different way. And over here, I have a pyramid pulled up, and we can see that if we slice it horizontally, we get like a square rectangle type shape. If we slice it vertically, we do get a triangle. But if we slice it at some other angle, we get trapezoids. So just from this pyramid, we could get three different cross sections. We can get the square rectangle, we can get the trapezoid, and we can get a triangle, all from the same pyramid. These practice questions are on point, lines, and planes. There's some on solids, but not too many. We'll do more in class, so please pause the video and think about what answer choices you would pick for the first two. For the first one, the correct answer is choice 3. AB and DH are on different planes. They're on different rectangles of the solid. So let me undo that. AE and DC are also on different rectangles. CG and EF are on different rectangles. But BC and EH are on the same diagonal plane from each other. You can connect them so that they are on the same rectangle. So they are coplanar. Correct answer for the second one is choice 4. Plane BAT is over here, and I don't know if it forms a right angle with that. Take a minute, pause the video, and try to think of an answer choice for these two questions. The correct answer for the first one is 1. Just like there is only one line passing through a point that is perpendicular to a line, same thing applies to planes. There would be, and I'm a terrible artist, only one plane containing point P that is perpendicular to line L. For the next one, pause the video and see if you can pick an answer. For the next one, I'm going to draw a little picture. So we have two planes, plane P and plane R. And it says that AB is contained in plane P, and it also says that it's perpendicular to plane R. So once again, I'm a horrible, horrible artist, but that means that planes P and R need to be parallel to each other because they are both perpendicular to the same line.